we basically have two branches of statistics. We have the descriptive statistics and we have the inferential statistics. The inferential statistics is actually that branch of statistics that helps us to use a sample data that was extracted from a population data to make conclusion and make decisions. Okay, at the center of the concept of inferential statistics, we have what we call the hypothesis test. Hypothesis test, as the name implies, is from just basically two words: hypothesis and word test. Hypothesis is simply an initial statement or an initial assertion regarding a population detail or a population parameter. It can either be right or wrong. So whenever you test an initial claim, an initial sentence, or an initial assertion regarding a population parameter, then we have hypothesis test. Okay, so we actually have a couple of steps that can actually be performed before you can actually be able to say you've made an hypothesis test. And the step one is for you to state the null and alternative hypothesis. Step two is for you to choose a preferred level of significance. Step three is for you to determine the direction of the test, either the left tail test, a right tail test, or a two tail test. Step 4 is to pick the appropriate statistical test for the analysis. Step 5 is to make your decision, and step 6 is to make the conclusion. My attention is going to be focused on step 4, and that is all about statistical tests. Now, we have a whole lot of statistical tests in the world of statistics. There are actually so much, and in today's video I'll be trying to touch each of those tests and when to use them. Please note that I won't be mentioning the null and alternative hypothesis for this test. Okay, that will be a separate video. So today's video is all about statistical tests and when to use them. Let's get into the video. When it comes to hypothesis test, most people come across just a single problem. Which test am I going to be using right here? Am I using a chi-square? Am I using an Anova? Am I using a z-test? So in this video, I will list all of the tests that I know and I feel you should know and when to use them. But before I start listing all of these tests, I need you to know that the test you're going to be using for hypothesis test is actually based on some couple of details, like 5 details. And the first one is the distribution. So we have what we call the parametric test, and we have the non-parametric test. So by parametric test, it simply means that those tests that are actually based on the fact that the distribution that defines your data set are actually normally distributed. That is, they have a bell shape. Now, for a non-parametric distribution, it means that the distribution of that data set or that sample data, it is not normally distributed, and the variable we are actually working with is actually more of a qualitative or a categorical or more of a positional variable. That is a variable that cannot be quantified. Now, the next detail that can determine the type of statistical test to use is what we call the size of the data set. So some tests actually work when we have large sample size. Some tests actually work when we have smaller sample size. So what is the threshold for large and small sample size? So basically, some statisticians use 30, some use 50. I'll be following the central limit theorem and be assuming 30. So when your sample size is more than 30, okay, we assumed you are having a large sample size, and when your sample size is lesser than 30 rather, we are assuming that you have a small sample size. Please note that this threshold can change. Some can use 50 and some can go as far as using 100, but for now I'll be assuming 30. The third detail that defines the type of statistical test you're going to be using is what we'll call the type of variable. So do you have a categorical variable or a numerical variable? If you can ask yourself this question and get the answer, then you obviously know the type of test that you need to know. If you want to know more about the types of variables we have in statistics based on categorical and numerical, I have a video right here that I'll be sharing for you that you can just check out after watching this video. Now, the next detail that can also determine the type of statistical test that you're going to be using is the parameters you're interested in. So by parameters, I mean those details that defines the population. So are you testing for mean? Are you testing for median? Are you testing for proportion? Are you testing for variance? Or are you testing for standard deviation? The type of parameter that you're actually interested in determines the type of test that you are actually going to be using. And the last detail that can determine the type of statistical test you're going to be using is the number of variable. If you have just a single variable to test, we have tests that can actually work on that. We call that univariate analysis. We are going to be testing 2 variables. We call that bivariate analysis, and we have tests that can handle 2 variables. And if you are going to be testing more than 2 variables, that is multivariate analysis. We have tests that can actually handle such number of variables. So these are the details that you can actually use to pick the right statistical test for your problem. So let's start by dissecting them one after the other. Please note that when a test is parametric in nature, there is a chance that it has an alternative non-parametric counterpart, in the sense that if I'm using test A, okay, and it satisfies the condition of a parametric distribution, there is a chance that I also have a non-parametric version of that same test, meaning if that test A does not satisfy the parametric conditions, then I can now switch to the non-parametric type. Okay, now I need you to know that in statistical analysis and in statistics in general, we try as much as possible to always favor the parametric distributions or the parametric test, because they are more accurate and more stable and can provide better evidence compared to their counterpart, which is the non-parametric test. So you are only advised to use the non-parametric test when you feel like there is nothing else you can do that can push you to use the parametric test. So I'll be starting with analysis of a single variable, and one of the most popular tests is hypothesis test for a single value of population mean. As you can see, in this test we actually have just one variable, and the parameter we are actually testing on is actually the mean, and this test can actually be used both on the parametric level and the non-parametric level. So if you have a sample size that is more than 30, okay, you're going to be using the z-test for one sample mean, and if you have a sample size that is lesser than 30, you're going to be using the one sample t-test, which is the t-test for one sample mean. So if you find yourself trying to test the value of a single mean, let's assume that your university is claiming that the average age of students in the university is 20 years old. So average age, mean, in this case of ours, is our parameter, and you feel like that sentence is wrong. So you want to test that the average age is either lesser than 20 or more than 20 or not equals to 20. So in that case, you're going to be performing an hypothesis test for a single value of population mean. And like I said earlier on, if the sample size is more than 30, you are going to be using a z-test. If it is lesser than 30, you're going to be using a t-test, and it's as simple as that. We can also test the hypothesis on a single value of population proportion, and the condition still remains the same. If the sample size is more than 30, you are going to be using a z-test. In this case of ours, we have just one variable, and our parameter is actually a population parameter. Now let's flip it and move to the non-parametric alternative for the hypothesis test for one sample mean. So if you remember your basic descriptive statistics, the mean can be used to locate the center of our data set. So the mean is quantifiable, and the counterpart in quotes of the mean is actually the median. So if you want to perform the non-parametric test for hypothesis test for one sample mean, we are going to be using what we call the sign test, which is obviously known as the hypothesis test on one median. So instead of testing for mean, we are going to be testing for median, and we used a sign test because the median is actually more of a qualitative approach to center compared to the mean, which is a quantitative approach to the center. And the sign test that we're going to be using to perform hypothesis test on a single value of the population median is going to be what we call the Wilcoxon sign rank test. Okay, and that is that about that. It's that simple, right? Very simple. Now we can also decide to perform hypothesis test on a single value of population variance or population standard deviation. Please note that when it comes to mathematics in general, we know that the standard deviation is actually equals to the square root of the variance. So most times we actually take them together. Okay, so the hypothesis test for variance and your standard deviation is actually still the same thing. And whenever you find yourself trying to test the value of a single population variance or a single population standard deviation, we are going to be using what we call the chi-square test for the variance. Okay, in this case of our parameter is either the population variance or the population standard deviation. We have just a single variable. Now let's talk about the hypothesis test for two variables, and I'll be starting with hypothesis test for two means. So if I have two values of population means and I want to test the difference between them, I can actually perform hypothesis test on the difference between these two means. Just like for one sample mean, it can either be a z-test or a t-test. So if we have a large sample size, we are going to be using the z-test, and if we have a small sample size, we are going to be using the t-test. I also need to state the fact that one of the conditions that we have to satisfy before we can be able to use a z-test is that in as much as the sample size must be more than 30, we also need to know the value of the population standard deviation that produced the sample. So because the samples were extracted from populations, and if you know the value of the population standard deviation, then definitely you can use your z-test. And if you don't know the value of the population standard deviation and your sample size is lesser than 30, then definitely you're going to be using a t-test. So hypothesis test for the difference between two population means can either be a z-test or a t-test, and the conditions of sample size and population standard deviation still remains the same. So when it comes to testing for difference between two samples, okay, we have to factor in the connection between the samples, and this is where the concept of dependent and independent samples comes into the picture. So by dependent samples, we mean the samples were collected from the same population. Take for example, I have a whole university, which is the population, then I extracted samples from different faculties in the university. So the sample, let's say from Faculty of Science and the Faculty of Engineering, there are two samples that are taken from the same population in the same university. They make up dependent samples. But if I take two samples from different population, then we have an independent sample. Take for example, I took sample from Harvard, then I took sample from Cambridge. The two populations are in no way connected or dependent on each other. So these two populations are actually independent on each other. Let us assume we are actually interested in getting the difference between the means of two independent samples. Please don't forget the fact that for independent samples, the samples are actually from different populations. So we are also assuming that the population standard deviation or the population variance of each of those samples are actually different from each other. Now, if you want to perform an independent sample test for the difference between two population means, we actually have to satisfy two conditions. Number one is that the samples must actually be independent on each other. Number two is that the population variance of each of the samples must actually be also different from each other. That is, they must not be equal. Once we can satisfy these two conditions, then we can actually use the independent sample test for the difference between two population means. Now, if we have the sample sizes and they are actually more than 30, then we are going to be using the z-test, or we know the value of the population standard deviations or variance of each of the samples, then we can actually use the z-test. And if we have the sample sizes to be less than 30, or we don't know the value of the population standard deviations, then we are going to be using the independent sample t-test for the difference between two sample means. Now, the non-parametric counterpart of the independent sample test, either the z-test or the t-test, is what we call the Wilkinson rank sign test, aka the Mann-Whitney test. Remember that for the independent sample test, either the z-test or a t-test, as far as the population variances are actually equal, we are actually testing for the value of the mean. So when it comes to the Mann-Whitney test, we are going to be testing for the difference in median. I'm sure you are asking me this question. So what if the population variances are actually equals to each other? At the same time, we actually have an independent sample. So what is the test we're going to be performing? Then in this case, we're going to be using the concept of the independent sample t-test for difference between two means, but this time we are going to be introducing what we call the pooled variance. So whenever we find ourselves in this sort of situation, we are going to be using a t-test to test for the difference between the two means, including a pooled variance. Now, what about getting the difference between the means of dependent samples? This is what we call the dependent sample test, aka the paired sample t-test. So whenever we want to get the difference between the mean of dependent samples, the test that we're going to be using is what we call the paired sample t-test, also known as the dependent sample t-test. We are using the word paired in this case because the two samples are actually extracted from the same population. So that means we are pairing one of the values in one of the sample with the values in the other sample. The non-parametric counterpart of this test is what we know as the Wilkinson rank sum test. We can also perform the test on proportions. It's not only the mean, and we can also have the independent samples, and we can also have the dependent samples. So if we have equal population variances, or we have equal population standard deviation for the proportions, and the samples are actually independent on each other, then we can actually perform an independent sample test for difference between the proportions. Now if the sample sizes are actually more than 30, that is, we actually have large sample sizes, then we are going to be performing a z-test, independent test on proportion differences. So what if we now have independent samples, at the same time the population variances in quotes of the proportions are actually equals to each other? Then we're going to be performing independent sample test on the difference between proportion, but we are going to be introducing the pooled proportions for the whole test that we are working with. I've actually not heard for the non-parametric counterpart of the test on the difference between proportions. If you've heard of it or you know about this, please go down to the comment section and drop them. Maybe we can learn one or two things from you. So we've talked about the z-test and the t-test for the past few minutes, and let us talk more about the chi-squares, even though I've actually mentioned one chi-square. So basically the chi-square is a non-parametric test. Anytime you hear the word chi-square is actually a non-parametric test, and it has a wide range of applications in the world of statistics and probability. Okay, so the first chi-square I actually mentioned was the chi-square test for variance. Yes, we actually use chi-square to test for variance, a single variance, and we also use the chi-square to test for a single value of population standard deviation. That being said, now chi-square have the chi-square I'll be talking about this case will be like just the two chi-square that I actually feel like they are the most applicable: the chi-square test for independence and the chi-square test for goodness fit. So let us start with the chi-square test for independence. So basically the chi-square test for independence is a non-parametric test that is used to test the strength of association between two categorical variables. By categorical variables, I mean those variables that can never take a numerical value. Take, for example, you are trying to see if there is a relationship between gender and the level of education. Now gender is a categorical variable, and level of education is also a categorical variable. As you can see, irrespective of the scale of the data set, as far as it is qualitative in nature, we can actually use chi-square to test for the relationship between these two variables, and the chi-square makes use of the observed value and the expected value to actually achieve this. Now before you can be able to like work with a chi-square, you need what we call a contingency table, also known as a two-way table. Okay, and the chi-square has certain conditions that must be met before you can actually meet it, and one of them is based on the fact that you must have a sample size more than 30, and the second one is that the expected value of each of the cells, okay, at least one of the cells must be more than 5. So that means the expected value of each cells must be at least more than 5. If you don't satisfy this condition, that is your sample size is lesser than 30 and the expected value of each cells, okay, it's not up to 5, then you are going to be using what we call the Fisher's exact test. I know you are asking yourself, so what is expected value? So basically the expected value is gotten from the observed value, which is the individual values that make up your data set. So there's a formula for calculating the expected value for each observed value in your data set based on the type of chi-square that you have. So for chi-square test for independence, there is a different formula. I won't say different, but there's a kind of a different formula for the expected value. And for chi-square test for goodness fit, there is also a different type of value. Now the chi-square test for goodness fit is a test for distribution. Okay, so in the sense that, let's assume in your university, okay, the school is saying that 30% of our students are actually Americans, 40% are white, 20% are Indians, and something like that. So the school is giving a distribution that defines the nationality or the race of students, and you feel like that is wrong. You feel like, we actually have more Africans in the school. Africans shouldn't be like 30%, they should be up to like 60%. And you took a sample from the school data and performed your own analysis in order to get your own distribution of students. Okay, so once you took your sample, you'll be able to like get out of like, let's say 400 sample, you can be able to like get 100 Africans, 50 are Indians, 70 are white, and stuff like that. So the test that you use to counter the school's claim about the risk distribution is what we call the chi-square test for independence. And like I mentioned, this test has its own expected value formula that's a bit different from that of the chi-square test for independence. So there are other ways we can use the chi-square, but these are the two most popular ones. Maybe I'll actually make a separate video for the other type of chi-squares that we actually have, at least test for contingency table. We have the McNemar's test, we have the G contingency table test, and all of those. Now let's move to the test for normality. So sometimes you actually have to test if your data set is normally distributed or not before you actually perform any test. In fact, this is the first test you actually have to perform before you start the process of hypothesis test, because if your data set is not normally distributed, you know what to do. If it is normally distributed, you actually know what to do. We have a couple of tests for normality, but the two most popular ones that I'll be mentioning, it's going to be the Shapiro-Wilk test, and we also have what we call the Kolmogorov-Smirnov test. Okay, so these two tests are actually tests for normality. They actually perform the same thing. They help you to determine whether your data set is normally distributed or not, but they have certain conditions that defines them. So you use your Shapiro-Wilk test rather whenever you have a smaller sample size. In this case, the threshold is 50. So if your sample size is lesser than 50, we are going to be using the Shapiro-Wilk test, and if your sample size is more than 50, we are going to be using the Kolmogorov-Smirnov test. So the Kolmogorov-Smirnov test is more or less like a more robust test that can actually handle large sample sizes, and the Shapiro-Wilk test is just for smaller sample size. So let's talk about the test for correlations. So basically, correlation is used to test the strength and direction of association between two variables, and the most popular correlations that we actually know is what we call the Pearson's correlation coefficient. So basically, this is a correlation that is used to test for the strength of association if your data set is quantitative in nature, that is, they are numerical in nature, and secondly, the data set is normally distributed. Okay, so since the Pearson's correlation coefficient is based on quantitative data, it means it has a non-parametric counterpart. That is, if your data set is not normally distributed and you're trying to get your correlation based on position or rank, not by the value of the variables. So this is where the Spearman's ranking actually comes into the picture. And the good news is that you can actually perform hypothesis tests on both the Pearson's correlation coefficient and on the Spearman's rank coefficient. We also have what we call the Cramer's V. Now the Cramer's V is more or less like, it's actually a parametric test, and it is basically used to test the strength of association between two categorical variables. Okay, and then we have the last one, which is the Kendall-Style test. So the Kendall-Style test is more or less like helping you get the strength of association between two nominal variables. Now the Cramer's V is more or less like a generalized version of the Kendall-Style, because the Kendall-Style is more about the nominal data set on the nominal scale. I'll be linking a video about the nominal interval scale right here. You can also check that out after watching this video. So the Cramer's V is all about categorical data all over, like all of them, and the Kendall-Style is like a subsection. It's focused on just nominal scale of data. Now let's move to the Anova. This is where it gets interesting. So we are going to be starting with the one-way Anova, which is like the most popular Anova that we know. But before I move to the one-way Anova, I have to define some things. I have to define the concept of dependent variable and the independent variable. Even though this is kind of like more of like a regression type of thing, you know, the dependent variable is what we call the predicted variable, and it's the variable you are trying to predict, and the independent variable is the variable that you are trying to use to predict the dependent variable. Okay, we use the letter Y to denote the dependent variable, and we use the letter X to denote the independent variable. So your one-way Anova is just how will I say this? It's just an independent sample test on steroids. Okay, so your independent sample test for means, okay, can only work for 2 samples. Now, the one-way Anova can actually work from at least 2 samples. So you can, if you want to compare at least 2 samples, okay, starting from 2, 3, 4, 5, you can actually use your one-way Anova to test for the difference between the means. So let's say in your university, an exam was done on a certain course, okay, and so we have year 1, year 2, we have the year 3, and we have the year 4. So the exam score right here is actually the dependence variable, okay, and we have like 4 levels, aka 4 factors. So year 1, year 2, year 3, year 4. If you want to test for the difference between the mean score across this level, we are going to be using a one-way ANOVA. If you are testing for just 2 levels or 2 factors, it is independent sample test, okay. So because you are testing for more than 2 samples, then the one-way ANOVA comes into the picture. One of the downside of the one-way ANOVA is that it doesn't tell you which of the score is different, but it lets you know that one of the scores is actually different from the other, but it will not tell you which is different. Now, ANOVA is also a parametric test in the sense that it assumes that the distribution that defines the data set is normal, okay, and the non-parametric counterpart of one-way ANOVA is what we call the Kruskal-Wallis test. Now, another rule that defines the ANOVA is that the levels that we are actually working on, each of the levels must be independent on each other. By independent, it means they are in no way connected to each other. Okay, so you can now ask me this question: so what if we now have dependent samples and we still want to perform a one-way ANOVA? And that is where the repeated measure ANOVA comes inside. So the repeated measure ANOVA is just a one-way ANOVA, but this time we are actually having the samples to be dependent on each other. Okay, we still have the normality condition standing, meaning it only applies when we have a normally distributed data. Now, the non-parametric counterpart of the repeated measure ANOVA is what we call the Friedman one-way ANOVA. Remember I said one-way ANOVA is basically used to test for the difference between the means of groups, right? Now, if this group you are talking about is actually now splitted into 2 groups, like we have 2 groups in the main group, then we can use the concept of a two-way ANOVA. So imagine us trying to test for this difference in score between those 4 levels, and across each levels we want to test for the difference in score for the agenda. So in the first level, male, female, the second level, male, female, the third level, male, female, the fourth level, male, female. So we have 2 categories on each level. So we are going to be using a two-way ANOVA to test for the difference between the score, exam score across each level, and difference in the exam score based on the difference in gender. Okay, I think that makes sense, right? Now, if you're having 3 levels, then you're going to be using what we call the 3-way ANOVA. Yes, we have the 3-way ANOVA. And if you feel like there is actually a form of covariation between the levels that we're actually working with, then definitely we use what we call the 2-way ANOVA if you have 2 levels, and you use the 3-way ANOVA if you have 3 levels. I hope I've not made this as complex as possible, but that's just it. I actually mentioned ANOVA right now. So ANOVA is just analysis of covariance, okay, which simply implies that just like I said earlier on, if you're trying to test for the difference between the mean of groups, and each group has a category, if you feel like they're actually a form of covariate or covariation between the levels you're actually working with, then analysis of covariates, or ANOVA for short, is something you are actually going to be using. We also have what we call the MANOVA, and the MANOVA is just a combination of ANOVA and regression analysis. So when you perform regression analysis at the same time you perform ANOVA, then you have what we call the MANOVA. Please note that ANOVA itself simply means the analysis of variance. I hope I've not made this as complex as possible, and I've been able to make it as simple as possible. So if you enjoyed this video and you learned something new from this video, and also make it to the end of this video, please give this video a thumbs up and also subscribe to this YouTube channel. Do you feel I missed something, or you have a question for me, or you want me to talk about a test? Please go down to the comment section and actually drop your questions or your comments. I'll be willing and be ready to attend to them. Thanks for making it to the end of this video, and we'll see you in the next one. Bye for now.